Good morning, December the 7th, and we've come to problem 19. We need to count the numbers here and to make a reality check, which I won't be able to do much about before having solved problem 20 probably. I started counting the points, or making a Mabel procedure for counting the points. And first the principle, and doing it step by step, taking a to 1 and the prime 7. Actually, I only assume that P is odd, so I make no assumptions as to Q being equivalent to 1 modulo 6. That will be in praxis. And then we make a set of squares, and then we count the solutions by simply for each x computing b. And then for testing, I print x and b so that I can distinguish which case we have. And that seems to work. We have 11 solutions there. Then I define it as a procedure. And test that it worked on the case I used to prove the principle. And now we can go about doing it. So first with 5 points, P equal 5. That's equivalent to 2 modulo 3. So I don't quite get it. Is that really true? Oh yes, it's when R is even, then Q is equivalent to 1 modulo 3. So we may not get Q plus 1. And then I could see that this formula would solve it. But with 11, I couldn't. Then I also tried different radii, and it turned out that they each had that was with 7, of course, or was it? Yes, with 7, I tried various radii, and they all had different results. No, not all. These two seem to agree, 3 and 4, and 2 and 5 agrees. So I believe 1 would agree with 6 as well. Well, that's for a reality check later on. So I like to have such a guy to be able to test the results. But now let's start on this problem. How well did we study section 2? It has the right form. Well, if we take the number of solutions to y squared being equal to b, and then for that b, multiply that with the number of solutions for x to the third minus a being equal to b, and then sum over b. And we are going to use the formula we actually proved it earlier on. I should have prepared that because I've actually forgotten it. I believe this was the case, and it only holds for a distinct from naught. I'll just make a short break to check that this is correct. Okay, it seemed that I remembered it correctly. That means we have to take out the cases a plus b vanishing and b vanishing separately. Here we only have, let's do it here. So that a is distinct from naught. So the number of solutions here is the sum of chi of a, chi to the third is unity, and the other case is a plus b vanishing, how on earth do we take that out? Oh, that means b equals minus a. In that case, the number of solutions to this guy is 1, and the number of solutions to this guy, and b does not vanish. So the number of solutions is the sum of chi of minus a, chi squared being trivial. Let's just forget about that for a moment and then write up the sum over all the other b's. chi2 and sum over chi3s. There's only one here, so we sum over these guys. That's summing over the 2 of order 3, of course. And that's a plus b. So we should sum over b as well. Now, in case b is naught, then this vanishes. So that doesn't give a distinct term. And when a plus b vanishes, then this vanish. So we can sum over all b. But then we have to add chi of minus a. Right. There's only one of, oops, this is the third order, this is the second order. Yeah, there is only one of order 2. So chi2 of minus a plus, plus, and we have 2 here, so it's chi3 of a plus chi3 bar of a, the other guy, plus overall b and chi's. So chi to the third equals unity. We work on the last term. That was not so good. It should have been a b here. Now what do? First we take chi of a out here. And then we must change sign on the b's. And here we must have b divided by a. Now watch that, that's chi, yes. now we can perform the summation over b, and this of course gives chi2 of minus a, which we see we have here. And that may be taken out. So we just sum over chi now. Chi of a and using the this should just have been chi. My index eraser. Oops, times dA of chi2, chi3 bar time to compare with what we should end up with. This seems very much to be what we've got down here. Yeah. So these two terms, well, they seem to be 3 now that I count them again. Why on earth should this give q plus 1? Getting this result indicates that I'm using an idea that ultimately works. So can we count these exceptions differently? The squares giving b, the squares giving naught, then we need to know the number of solutions to this equation. And when b, I'm missing something because this will only give very few solutions. Not q, never q plus 1, except when q is very small, of course. So we could get like 1 or 3 solutions to this equation. If say a doesn't vanish, so it's none or 3 solutions to this guy. When q is equivalent to 1, then the map is 3 to 1 in general, with 0 being the only exception. And when Q is odd, then we also have that x mapping to x squared is 2 to 1. I think I shall have to read the section, or the part of the section again, and then see if I'm missing something that way, because I don't get any ideas by looking at it. As soon as I looked at the derivation in the book, it stood out that one has to sum over two characters of order 2, namely chi2 and the trivial one. And the same with chi of order 3, we have to take the trivial guy into account as well. When we choose the trivial of chi2, the trivial one of order 2, the trivial character here, then when this is non-trivial, the sum will always vanish when it's non-trivial. So we can forget the trivial one when summing over the chi of order 2, or the characters of order 2. But we have to take it into account later on. I'm wondering if we choose the trivial character here, wouldn't the sum of this vanish? It should. Except when they are both trivial. So my claim is that all I missed was both being trivial. And in that case, the result should be, I think it was Q minus 2. Exactly. So I think, if we add Q minus 2, then we have chosen all cases when one of them is trivial. So we just have to add it all the way. We are getting close. what I need is to take the cases I was considering up here and find out that there will always be 3 points there. That sounds strange. Really? Well, I'm getting closer. But the fine count didn't quite give the right result. Well, guys, I have looked at this again and done some homework, always a good idea. I mean, homework, it's fixing things in the house. And then when I looked at it again, I realized I was far too careless up here. I think I've already mentioned that we need to take the trivial character into account. And that means adding 2. Then I took, now if we choose the trivial character here for chi2, for the one where chi squared is trivial, then that actually gives naught at B, and that means that we fail to add chi of A. So that means when we disregard the trivial character down here, we have to subtract the values we get from chi of chi 3 of A and chi 3 bar of A. So these two guys cancel. And the same thing happens when we take the trivial character for chi here. When A plus B is naught, it's not added, and that means we get minus chi 2 of minus A, which eats this guy. Therefore, we are left with these 2 added terms, and they just give 2. So it's 2 plus, and now it's equal. So we just have to delete 2 down there. There we go. And the final icing on the cookie is that this is the number of affine points, and this is number of projective points. So we had to add the point at infinity, which is 0.1.0. That was problem 19. So conclusion here, I forgot the trivial character, And then when I remembered it, I didn't handle it with sufficient care.